Okay, we're going live here. We're making this recording. It's exponential functions, t-table graph style. As you can see, I have my calculator turned on, and I'm just so you know, I'm in classic mode. I'm in classic mode. Just in case you don't have a newer calculator, I want to make sure it works for everybody this video. So here's what we're going to do. We are going to graph some exponential functions, and an exponential function looks like this. This guy right here is called the base. This guy right here is called the scalar. And they can be any numbers I want to use. And of course, I'm going to plug in numbers for x. I'm going to get out numbers for y. I'm going to plot some points. I'm going to connect some dots. And what you're going to find is every exponential graph has the same type of look to it. It really does. So part of what we're doing today is you're trying to get used to what do they always look like. So here we go. I'm going to start with one where I say y equals 5 to the x. This is going to be my first example. So I want to draw a picture of this thing. Now, just so you know, if you want to check your answers to see if they are correct, you're going to go to y equals, you're going to say, y equals 5 to the power of x, 5 to the power of x, and you're going to hit graph. Let's see, get that a little closer. There we go. That's what your answer is going to look like. It is totally true. In fact, you're going to make a table of values. Right above the button that says graph, there's a little in blue, it says table. So I'm going to go second graph, and look, I get this thing called the table. Now, you'll notice that their table has a 0 dead center here, and then it's got some negative numbers on this side. It's got some positive numbers on this side. So when we're going to graph this, I want you guys to make some table of values for me, or you could steal them right off this table here. You could. But I just want you to get kind of used to the rhythm of how these things are graphed. So you don't need to plug in 5 negative values. You don't need to plug in 5 positive values for me to give me a decent graph of this thing. You don't. But I do want you to have the general concept, what the shape of this thing is. So once again, if I go back to graph, that is the general shape of this graph. It is an exponential curve. And by the way, this thing would be called exponential growth because it's rising on the right. Now, hey, just so you know, I have a follow-up video that will have all of this information in one spot. So this video is basically, let's just practice plugging numbers in the calculator and checking our work. That's what we're getting accomplished here. So I'm going to turn this, turn it off for a second here. And here's what I want you to do. I want you to, of course, grab a ruler so it's pretty. And you're going to make a table of values called a t-table. It looks like the letter T. Whoops. You're going to plug in some x's. You're going to get out some y's. That's what you're going to do for me. When you get that done, you are going to graph this thing. Now, when you graph this thing, of course, we have an xy coordinate system. So I'm going to make it look as pretty as I can. Whoop. There we go. And I want you to use these numbers, -2, -1, 0, 1, and 2. You're going to plug in -2, -1, 0, 1, and 2. You will plug those numbers in. Now you're going to get output. Well, let's find out what we get. I could go to table. I'm just going to say, but if I did 5 to the power of -2. So remember, -2, 5 to the power of -2. I get 0.04. That's a very tiny number. How about when I do 5 to the power of -1? 5 to the power of -1 gives me 0.2. Now remember, negative exponents, what do? They cause this number to go to the bottom, since this would be 5, right? 5 over 1. But it's converting it to a decimal for you, and that's fine. You're going to find when we do the assignment, I'm going to just have you use decimals. And then 5 to the power of 0. Any number to the power of 0 is 1. It is true. Any number. I don't care what it is. 75 to the power of 0. It's 1. 2.658 to the power of 0. It's 1. Any number to the power of 0 is 1. So so guess what? That's what we got for that one. Now, I don't even need a calculator for this part. What's 5 to the first power? If I plug in 1, I'd get 5. And 5 to the second power, that's 25. So here we go. We're going to sketch a quick graph of this. When I plug in -2, I get out a very tiny number. Well, if I'm going to graph, let's say that's 1, that's 2, that's 3, that's 4, that's 5, 0.04 would be hugging that line. It would be right on the line. It would. And if I plugged in -1 and I got out 0.2, that would be like real close to the line too, a little bit farther off. If I plug in 0, I get out 1. I plug in 1, I get out 5. Now, I plug in 2, I'm already at 25, which is way off the charts. Look, I mean, 25 would be way up here off the page. So you don't have to go crazy for me. What I'm hoping you see is this nice, smooth curve. And of course, on this side, it's just going to keep getting steeper and steeper and bigger. But on this side, what's going to happen, what's going to happen is this thing is going to get closer and closer and closer to the x-axis. But it's never going to become a negative number. It's never going to become a negative number. If I plug in -3 for x, if I plug in -4 for x, I'm going to go back to my calculator, show you on the table. Look, when they plug in -1, they got out 0.2, then 0.04, 0.008, and then it does this e thing. Remember, I told you when your calculator says e, it's trying to, it's trying to calculate something that is super duper duper tiny, because that's scientific notation, 3.2 times 10 to the -4. What I'm trying to get at is this. These numbers that keep coming out are getting tinier and tinier, but one thing they are not negative, which means I have an asymptote in my graph. Right here on the x-axis, there is an asymptote going through here. So the x-axis is like where my boundary exists for this function. On this side of things, like the farther and farther I go this way, the steeper and steeper this graph will get. But on this side, it's tinier and tinier and tinier. So this will be an asymptote. Guess what? All exponential functions that we will graph will have an asymptote. And that asymptote will be right here on the x-axis. It's going to be our boundary line. I like to think of it as that's the floor. You're not going to pass through the floor. You're just going to hover right above it. So let's try another one. We're going to take a look at this guy. Here's my second example. And guess what? I'm going to make a table of values. I got x's, I got y's. I'm going to plug in the same exact numbers every time. -2, -1, 0, 1, and 2. And this time I'm plugging them into a fractional idea here. So let me clear this out. I'm going to plug in parentheses 3/8 to the power of -2. Well, what the heck is that? I get 7.1111. So you know what? When we get these repeating or weird decimals, let's just call it 7.1. We'll just round that thing off. And then let's do parentheses 3 divided by 8. We're going to take that to the power of -1. And boom, what do I got? 2.6 repeating. So I'm just going to call that 2.7. Let's round it off. 2.7. If I plug in 0, heck, I'm going to save myself a little work. I plug in 0, I'm going to get out 1. No matter what, you take any number to the power of 0. Well, it's a fraction. Yeah, go ahead. Let's see what happens. Bam, it's a 1. Now, 3/8 to the power of 1 is 3/8. But if we're going to work in decimal, let's just keep doing it. That would be what? 0.4 if I rounded that thing off. 0.4. We're just going to round off all decimals. And then 3/8 to the power of +2. I get 0.1406. Let's just call that 0.2. No, sorry, 0.1. If we rounded that off, it would be 0.1. So here we go. I got 0.1 when I did that. Now, all my values I calculated are right here, just so you know. You can always go second graph, and you'll see all my numbers there. I just have to round them off. But remember, the calculator goes 5 above, 5 below. We're just doing a couple above and below here. But look, we would have the same exact stuff. Oh, wait, that's not the right graph. Crazy me, sorry. I'd have to plug in the actual graph we're working on. 3 divided by 8 to the power of x. Okay, now my table of values. Whoops, my graph. What? Look at my graph. By the way, that is the answer. So let's see here. If I look at the table, see, there's my answers. There's the same ones I got. Look, rounded off, 7.1, 2.1, right? The table's a nice shortcut. Some of you guys are going to just go, I'm going to use the table. Okay. Here we go, though. Let's plot some dots. If I want to start this off, remember, I am plugging in the same information each time for this. I'm going to plug in -2, -1, 0, 1, and 2. Those are the ones I plugged in. When I plugged in -2, starting on the far left, I got out 7.1. Now 1, 2, 3, 4, 5, 6, 7.1-ish. So that would put me up right about there. Okay, that's not too bad. You know, if you have to make more than 10 dashes, please don't. You can just estimate and tell me it's going really big time over there. That's okay. When you are showing your work, like here, -1, I plugged in -1, I got out 2.7. See, 2.7, you don't have to make it this perfectly. I'm going to count by tenths. Don't worry about it. I will get it that you estimated the location of that value. That's okay. Plug in 0, get out 1. Hey. Plug in 0, get out 1. Plug in 1, get out 0.4. That's about right there. If that's 1 unit, that's about 0.4 units. Plug in 2, get out 0.1. Now what's happening here is, look, it's going to get really steep on this side, but over here it's going to hug the line. So once again, this guy's just going to get big, big, big. It's just going to get bigger, but this time it's going to cut down this direction. Over here, it's going to become asymptotic. It's going to become asymptotic to the positive side of the x-axis this time. So we want to make sure somebody knows there's an asymptote there. So we put a dashed line in our work. That's how you mark an asymptote for somebody. I will ask you to do that when you graph. And then on this side, it's going up. Well, just a reminder from Algebra 1, because you did do this in Algebra 1. If it goes up on this side, it means it's got to be going down on this side. So in algebra, we would call this a decay model because it's going down on the right-hand side. Here's my last example. Look, it was going up on the right-hand side. So this would be called growth. And that's something they showed you in Algebra 1. Don't worry, I have an outline for all of these terms and vocab words and things like that. What do we need to get accomplished today? Well, we've got to get graphs drawn. That's what I want to make sure we can do. So that was my second example. I wanted to show you guys that sometimes your graph will rise on the right, sometimes your graph will fall on the right. And you're going to plug in the same numbers every time, and we're going to round off all this stuff to the nearest tenth, just to make it easy, okay? Plot some dots, connect some dots. Just remember, you're going to get some asymptotic behavior from this. Now, here comes my next example, which contains a scalar. All right, here comes my first example where I have a scalar. What is a scalar? A scalar is a number that amplifies your graph there. It's going to embiggen this graph by a factor of 20. Well, what? Look, we're still going to plug in -2. We're still going to plug in -1. We're still going to plug in 0, 1, and 2. Those are still going to be our input. But our output is going to get multiplied by 20. Now, you'll also notice, here's my coordinate system I'm going to use. This is my x-axis. Here's my y-axis. But why did I write it this short or this? Well, because I only have 2 dashes on this side, so I don't need a lot of room. I only have 2 dashes on this side, so I don't need a lot of room. And I'm going to tell you, no matter what we do to this thing, it will still have an asymptote right here on the x-axis. It's going to have a boundary marker right there. That asymptote, this graph is never going to go below that line. So I don't need a bunch of information down here, so I'm going to be a little bit lazy since I can be. So when I graph this one on the calculator, I'm going to go back, clear all that out, and this time I'm going to say 20 parentheses 2.4 to the power of -2. I'm just going to punch it in exactly how I see it. So it's 20 times 2.4 in parentheses to the power of -2. What do I get? I get 3.47 blah, blah. I'm going to just round it off nearest tenth. So I'm going to call the output the y value, or in this case, they're using g of x. I guess I could have said g of x. 3.5. Let's call that thing 3.5. Let's do the next one. I'm going to do 20 parentheses 2.4 to the power of -1. What am I going to get? 8.3 repeating. Let's just call it 8.3. Now, here's the fancy one. 20 parentheses 2.4 to the power of 0. Now, what's supposed to come out of here? Anything to the power of 0 is 1. Hey, how come my answer's not 1? Well, because you have a scalar. Your graph is going to be amplified by 20. So order of operations, your calculator is saying this part is the same as 1. Take this to the power and then multiply it by 20. So that's why your answer is 20. Now, the next piece, 20 parentheses 2.4 to the power of 1. Well, it's the same as saying 2.4 times 20. And I get 48. I don't even have to round it off. I'm just going to call that thing 48. Now, here's the dealio with this. Last one, 20 parentheses 2.4 to the power of 2. Let's see what this turns out to be. 115.2. Now, 115.2. Now, if I want to sketch this graph, now I'm going to show you this on the calculator because you're going to go, man, that's... I'm going to go to y equals. I'm going to get rid of my last one. I'm going to punch in 20 parentheses 2.4 to the power of x. So I punched it in. I'm going to hit graph and watch what it does. There's my asymptote, but then, whoa, it goes way up. What the heck-a-rooney? Well, look, here's what happened. I could move up there and find that it crosses at, that it crosses at y equals 20. It does. That's where it intersects the y-axis. But how do I see that? Well, look, remember, I'm looking at just this picture, which is a tiny little rectangle. The graphing calculator refers to this thing as a window. So if I hit window, look, I want to show you something. There are 10 dashes on the negative side of the x-axis. You know what? We're only using 2 of them, so I'm going to change that up, and I'm just going to put a -2 there and delete at 0. There's x min, -2. I'm going to go here and change this to a 2. We only have 2 dashes on the positive side of the x, and every dash on this x is worth 1 unit. Okay. But look, do we even need anything in the bottom? We have nothing below the x-axis. So I'm just going to say y min. You know what? I'm going to say -2, just so you can see a little sliver of light there. But here's the deal. My maximum value that I got out when I plugged stuff in was 115. So I'm going to say, you know what? Let's make this 115 y max. And you go, what? Well, that'll give me the top answer. But here's where I'm going to change things. Y scale. Y scale. Y scalar. See, this thing is called a scalar in mathematics for a reason. I'm going to make every dash on the y-axis worth 20. So what did I do? I just went to my window and I changed some values. Well, I only need 2 dashes on the left, so -2 for x min. I only need 2 on the right, so 2 for x max. I left my scale alone. I'm not going to change the scale. Every dash on the x is worth 1 unit. But when I did the y, well, I want to see a little bit of the y-axis, but I went up as high as my graph goes, and I made every dash now worth 20 to adjust the scale. Scalar. That's what it's called. Let's hit graph and see what this looks like. Boom. And it goes up, 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 Jetson. There you go. Now, here's what I want you to do. I want you to embrace the fact that your calculator, you can manipulate this window to look any way you want. But let's do that on paper, because you're not going to turn the calculator into me for the assignment. You're going to turn in the paper, or take a picture of the paper. So here's what I want you to think. When I graph this, instead of 1, 2, 3, 4, 5, instead of counting by ones, we're going to count by whatever this guy says. I'm going to make this worth 20. Scalar. This will be 40. 60, 80, 100. What the heck? I could go one more and go 120. So let's see. If I adjust the scale for the scalar, when I plugged in -2, I get out 3.5. Well, if this is worth 20 units, then 3.5 would be way down here. You see what I mean? I plug in -1, I get an 8. Look at that. Fresh. When I plugged in 0, I got out the scalar. I plugged in 1, I got out 48, so that would be about here. I plugged in 2, I got out 115, so it'd be about here, right? I still get to preserve, whoops, make that a little bigger. I still get to preserve what my graph looks like. My exponential graph, I can make it so that all of them have a very similar vibe. They look similar because I can adjust my scale. I totally can adjust my scale. Now, once again, I have an outline, an overview of all this stuff. You're going to find it in the last video I post for this topic. But these are just examples because I knew I had to do it live with the calculator. So anyway, that's my third example. This is the first time I had a scalar, but whatever that scalar is, that's going to adjust my scale. So it's very easy. And what do? This is just me rounding off some decimals, and this is me plotting those points. That's all I'm doing. Let's look at one more example like this. So I'm going to show you my last example. And as you can see, I'm going to have some x information I plug in. Guess what? I'm going to use the same numbers every time. -2, -1, 0, 1, and 2. I'm going to get y information out. I'm going to round it off to the nearest tenth so I don't have to play with big old chunky decimals. Let's get some perspective here. What's my scale going to be this time? 100. Whatever that number is, that's my scalar. I'm going to use that for the scale on the y-axis, not on the x. So let's talk about this right here and now. I am still only plugging in -2, -1, 0, 1, and 2. I am not changing what I plug in for x. So I will never change the x scale. The scalar, this guy's job here, the scalar will tell me this should be 100, this should be 200, this should be 300, this should be 400. That's the scalar's job. The scalar helps me adjust the y-axis, not the x. So I'm going to end up with an asymptote here. I wish I had a different color pen, but I only have blue right now, so that's it. So I'm going to plug some stuff in here. But before I forget, because if I want to check my answers, I can. But my window is all messed up. It's set up for the last problem. So I'm going to zoom standard. Watch, I'm going to go zoom, and then that's number 6 on your keypad, number 6, zoom standard. And what happens? It goes right back to normal. Or let's look at that window. Let me show you. I hit the window button, and it's all back to 10s and everything. Don't worry about this junk on the bottom. Don't worry about it. This is where we do all our changes, okay? So I'm going to get some numbers here. I'm going to quit this screen. I'm going to clear this out, and I'm going to start entering some stuff. So I'm going to do 100 parentheses 1.4 to the power of -2. So I punch that in, I hit equals, I get 51.02. I'm just going to call it 51. If I round off to the nearest tenth, that's 51. Now, if I plug in 100 parentheses 1.4 to the power of -1, what do I get? I get out 71. So I'll go, okay, 71.4. Let's call it 71.4. Now, do I really need to punch this one in? 100 parentheses 1.4 to the power of 0. What's the answer going to be, people? I think it's 100. There it is, 100. You get out the scalar. And then I'm going to do 100 parentheses 1.4 to the power of 1. I don't even have to do to the power of 1 because it's the same as 100 times 1.4, which gives me 140. And then let's see what our last chunk of the puzzle is. 100 parentheses 1.4 to the power of 2, and I get out 196. I'm just going to write it down. So I got all my input was the same as always. When I graph an exponential, I always use these numbers because they always give me enough information. That means I don't have to work really hard to graph it. And look at all my output. There it is. Remember, I'm going to use the scale of 100. So that'll be 200. That'll be 300, etc., etc. But take a look at this. I wanted you to see something about this number here. When I plug in -2, I got out 51. So that would put me about right there. I plugged in -1, I got out 71. So I'm about right there. That's what I get out when I plug in 0, I get out 100. I plug in 1, I get out 140. When I plug in 2, I get out 196. So what happens is it almost looks like a straight line. It really does. It's super laid back. If I just connect these dots, that's all I see. But I want you to understand this. When you're graphing something that's exponential, the closer this number, this is called the base, the closer the base number is to 1, the more laid back your graph will be. The closer this number is to 1, so 1.4 is almost 1, it makes my graph relax. It doesn't get steep as quickly. Now, will it keep going up? Yes, it will. Will it become asymptotic over here? Yes, it will, but it's going to take a little bit longer for that to occur. But I can totally check my answers with the calculator, which is something I'm trying to get you guys to understand. So here we go. I am going to clear all this junk out. I am going to go to y. I am going to clear this last function out. I'm going to put 100 parentheses, 1.4, close it, to the power of x. So make sure you've entered in your graph the same as mine. Okay, now if I hit graph right now, remember I just did a zoom standard. If I hit graph, I'm not seeing much at all. In fact, it's way over here. Well, heck, that's because I really stretched this graph out. I really stretched it out. So how do I make it look like this? Well, let's go to the window. So I'm going to go to the window. Now, once again, my x's, I only plugged in -2 dashes. I'm going to hit delete right there. X max, I'm going to make that say 2, and I'm going to delete this. My scale on the x-axis never changed. It's still 1, but I don't have anything below the y. I have an asymptote. There's nothing down here. So I'm going to make that, I'm just going to give it a little sliver of light there. I'm going to say -2 and get rid of, delete that, 0. And then y max. Well, what's the highest value I got out was 196. So I'm going to make it 200. I'll just make the top end 200. But what's the scale I want to use? What is the scale? Whatever the scalar is. So whatever, if this was 10, I'd make the scale 10. If this was 15, I make the scale 15. If this is 25, I make the scale 25. So I'm going to make my scale 100. Every dash on the y is worth 100. And then if I hit graph, you're going to see my laid back graph, just like I have it here, coming into view. Look at how pretty that is. Are you kidding me? What? Now, once again, there's more activity on this side. It's going to keep going up, but it's going up slowly. On this side, it's going down, but it's going down slowly. So my actual hand-drawn graph shows the information that the window does not provide here. But what do you get? You get something that is this called decay or growth? Let's talk about that. Is that decay or growth? This would be growth because it's going up on the right. If it goes up on the left, it's decay because that means it's fallen on the right. But that'd be a growth graph. And I've got every piece of information that I need all in one nice little part there. So when you guys get to the end of these 3 lessons or 3 videos, first video is how to graph an exponential. Second video is going to be how to graph a logarithm. And then the third one is going to have the practice, and it's going to have an outline of my notes for this stuff. So that's all we have for this one. That's a lesson on graphing exponentials using a table of values. Okay. Catch you later. Bye-bye.